Welcome to The Explainer. Today, we're diving into a seriously fascinating engineering masterclass. When you look up at the night sky, it seems so peaceful, right? Well, for the spacecraft up there, it is anything but. We're going to explore exactly how we navigate the incredibly harsh, completely unforgiving environment of space. It's a journey into the hidden mechanics of spacecraft survival.
So I want you to start by asking yourself this. How do you steer a vehicle when there is absolutely zero road to push off of? Think about it. There's no air for wings to bite into, no water for a rudder, no ground for your tires. We're dealing with the bizarre, completely frictionless reality of spaceflight physics. Up there, even the tiniest little push will keep you spinning forever, unless, of course, you do something about it.
Okay, so here's the game plan for today. We're covering the spacecraft pointing problem, momentum as a space commodity, designing the spacecraft spin, navigating disturbance torques, and finally, the tools of control.
All right, let's kick things off with part one, the spacecraft pointing problem.
Imagine trying to precisely aim an antenna at a tiny little ground station on Earth. But at the exact same time, you have to keep your solar arrays locked directly on the sun and keep your thermal radiators pointed out into deep space so you don't overheat. It's an insane 3D puzzle. Well, managing that whole shebang is the Attitude Control System, or ACS. It's the vital, overarching system designed to orient the main structure of the spacecraft correctly and to the exact required accuracy. Whether you're aiming a comms dish or pointing the Hubble Space Telescope at some distant galaxy, the ACS is the brain and the muscle making it happen.
Moving right along to part two, momentum, a space commodity.
Okay, to truly get how the ACS works, we kind of have to stop thinking about turning a steering wheel and start thinking about physics. There's this great quote from our source material: "Angular momentum is a commodity that can be acquired and disposed of or stored." I absolutely love this analogy. In space, angular momentum is literally like currency in a bank account. A spacecraft has to constantly budget this currency. If a tiny external force pushes on the craft, well, it deposits momentum into the system. And if the spacecraft doesn't have a way to store or spend that momentum, it's going to start tumbling completely out of control.
So how do you manage that physics checkbook? It's done through this fascinating sequence called the momentum dumping process. First, internal torque motors spin up to correct any tiny pointing errors. As they do that, the external momentum is absorbed and stored inside a spinning middle wheel right inside the spacecraft. But eventually that wheel is going to hit its maximum permitted speed. The momentum bank account is completely full. When that happens, the spacecraft fires external gas thrusters. This applies an outside force, allowing the internal wheel to safely spin back down to its normal speed without knocking the satellite off course. They are quite literally dumping the excess momentum overboard.
Which brings us to part three, designing the spacecraft spin.
Because of how all this momentum stuff works, engineers actually have to choose very specific geometric architectures. First up is the 3-axis stabilized spacecraft. Now, this non-spinning layout basically looks like a rigid box, but those massive solar arrays sticking out, they are actually incredibly flexible. Because the main body doesn't spin, any movement at all can cause those long panels to flex and wobble. Engineers literally have to program their ACS computers to model up to 20 different flexure modes, just to make sure the satellite doesn't shake itself apart every time it makes a turn.
Now contrast that rigid box design with a dual-spin spacecraft. Notice the big difference here. A large portion of the spacecraft is constantly rotating on a bearing, while the antenna section stays completely still so it can keep pointing at Earth. Why do it this way? While spinning a massive part of the craft creates what's called momentum bias. It provides an incredible amount of gyroscopic rigidity, making the spacecraft super resistant to getting pushed off course. It's exactly like how a spinning top just refuses to fall over.
But spinning architectures introduce a brand new nightmare: nutation. Nutation is basically an oscillatory coning motion, or really just a wobble, that happens in spinning spacecraft. Now, remember, the vacuum of space doesn't have any atmospheric friction, so if a satellite gets bumped and starts to wobble, that wobble will literally last forever. No joke, it will never naturally slow down unless engineers deliberately step in and kill the motion.
And how do they kill that wobble? With two seriously ingenious methods. On one hand, we have passive damping. This is brilliant because it's so simple. Engineers install these ring-shaped metallic tubes and fill them with a viscous fluid, like alcohol or freon. As the spacecraft wobbles, the fluid sloshes around inside, and that internal fluid friction slowly bleeds off the kinetic energy, calming the craft down. On the other hand, we have active damping.
This is where the spacecraft's computer actively detects the wobble using sensors, and then commands torque motors to fire these perfectly timed, proportional reverse torques. It basically punches back to forcefully cancel out the motion.
All right, let's jump to part 4, navigating disturbance torques.
So you're probably wondering, what exactly is bumping these satellites in the first place to cause all this wobble and momentum buildup? Well, it turns out the hazards are completely invisible. If you're under 500 kilometers, there are actually enough stray air molecules up there to create aerodynamic drag. But look at what happens further out. Between 500 and 35,000 kilometers, variations in Earth's gravity and magnetic fields are physically grabbing and twisting the spacecraft. And get this, above 700 kilometers, solar radiation pressure becomes the dominant force. Yes, the actual photons of light from the sun act as a continuous physical force pressing against the solar panels, just like wind catching a sail. Crazy, right?
And finally, part 5, the tools of control.
Okay, so if the spacecraft is being constantly pushed by sunlight, pulled by uneven gravity, and dragged by stray atmosphere, how does it fight back? Engineers break the hardware down into 2 main categories: internal and external torquers. Internal tools, like reaction wheels, are super accurate and don't use a drop of fuel. They just spin up and down using electricity. But, like we talked about earlier, they eventually fill up with momentum. That's exactly why spacecraft almost always need a combination of both. You need the external torquers, like gas jets or magnets, to push against the outside environment and dump that momentum. Gas jets work everywhere, but, they eventually run out of fuel. Magnets use no fuel, but they rely on being close enough to Earth's magnetic field to actually work.
And speaking of magnets, just think about the incredible physical reality of these devices. These are magnetic torquers. Specifically, they're massive, meter-long metal rods that were used on the Erica spacecraft. By running electrical current through coils wrapped around these rods, the spacecraft generates its own magnetic dipoles. It essentially turns itself into a giant compass needle that physically pushes off of the Earth's own magnetic field to turn the spacecraft. It is an absolutely brilliant workaround because it uses zero physical fuel. That gives it a virtually unlimited lifespan, as long as those solar panels keep providing power.
But, and there's always a but, there is a massive catch. It's a constraint engineers call the equatorial blind spot. Because of the laws of electromagnetism, magnetic torquers cannot produce a twist, or a torque, along the direction of the local magnetic field line. So since Earth's magnetic field lines lay perfectly flat running north to south right at the equator, a satellite orbiting precisely over the equator literally cannot pitch itself north or south using just magnets. Engineers actually have to mathematically plan out these complex coning maneuvers just to overcome this one geographic physics constraint.
Which brings us to our final thought for this explainer. Knowing all of this now, the complex 3D puzzles, the constant budgeting of momentum, the invisible pushing of sunlight, and these massive internal metal wheels spinning up and down, how are you going to look at the night sky tonight? Every single point of light moving up there, every satellite bringing you GPS or internet, is fighting a continuous invisible battle of physics right this very second just to look down at us. It truly is a masterclass in engineering.